So here's a couple of opportunities to practice the ratio test. So first with the series from 0 to infinity of 3 to the n over n factorial. Factorials are going to be the main giveaway to when we should go straight to the ratio test. If you see a factorial, then ratio test should be the first thing you think of. So if we apply the ratio test here, so the way it works is you take the limit as n approaches infinity of the absolute value of the n plus 1 term over the nth term in a series. So in the case of example A here, that would be the limit as n approaches infinity. So with the n plus 1 term, get another color ready. So with this a n plus 1, you should substitute n plus 1 in place of each of your n's. So this should be 3 to the n plus 1 over n plus 1 factorial. Okay, so there's your a n plus 1 term. Over nth term, you just copy what you see. N factorial over, 3 to the n over n factorial. Now, one thing to notice here, everything is positive. Power of 3 is going to be positive. Factorials are always positive because they're by definition product of positive integers. So everything here is positive. I can drop the absolute value then. It's not doing anything to this expression. Also, instead of dividing by a fraction, I can multiply by the reciprocal. So now I'm going to write this as 3 to the n plus 1 over n plus 1 factorial, that's the n plus 1 term, times the reciprocal of the nth term. So I'm going to bring this up and flip it over, so n factorial over 3 to the n. And you may, once you apply the ratio test a few times, you may start going straight to this step here, which will be fine. So instead of dividing by the nth term, multiply by the reciprocal. Now we want to simplify this a bit. And you may be comfortable simplifying it in the form it is there. If you're less comfortable with that sort of thing, then what you can do, sorry, I know it's a little dark here, but so take things like the 3 to the n plus 1 right here, and write that as 3 to the n times 3 to the first. That's equal to 3 to the n plus 1. Also, this n plus 1 factorial right here, we want to simplify that. We're comparing it with n factorial. Remember that when you simplify factorial expressions like that, you always leave the smaller factorial alone, which in this case is going to be that n factorial. Expand the larger one, and so we can rewrite it in terms of the smaller one. So n plus 1 factorial, that would be n plus 1 times the positive integer that comes right before n plus 1 would be n. So at this point, we could just write n factorial. And so n plus 1 factorial is equal to n plus 1 times n factorial. That's something that you'll use frequently in these problems, times 3 to the n. And now we get to reduce. So 3 to the n goes away, n factorial goes away. And so we see that we're taking the limit as n approaches infinity of 3 to the first over n plus 1. So that has the form some finite number over infinity. Limits of that form are always going to 0. Okay, so ratio test, we need to think about the way ratio test works now. When the limit is less than 1, strictly less than 1, then we can conclude that the series converges. And not just converges, but converges absolutely. You get absolute convergence for free with the ratio test. But so this example A right here converges by the ratio test. Okay, so that's A. We now need to solve example B here. So I'm going to get rid of this. And I should have left that first limit there because that'll be the same. I'm going to apply the ratio test to this one as well. There are other tests you may apply, but like the root test, which you're going to cover next, you can't apply the geometric series test straight away with this thing because it's not a geometric series. Geometric series has to be just a constant times a constant raised to the n. You can't have, this is not a constant, so this is not a geometric series. Ratio test does also work well with exponential expressions though. So I'm going to apply ratio test also to example B here. So the limit as n approaches infinity of the absolute value of the n plus 1 term over the nth term, this is just the way the ratio test works, in this case will be the limit as n approaches infinity of, okay, so again I'll write the n plus 1 term in red here. So the n right here gets turned into n plus 1 times 7/8. In place of n there, we put n plus 1 over an, which again with an you just copy down exactly what you see in your given series there. Here again, everything is positive. 7/8 positive, base raised to any power is going to be positive. N is all throughout this chapter is a positive integer. So I can drop the absolute value again, like I did in that last example. Yeah, okay, and that's mostly all I'm going to do here. So n plus 1, if you like, you can take this 7/8 to the n plus 1 and write it as 7/8 to the n times 7/8 to the first. That's just if it helps you better understand how to reduce this thing. Over n times 7/8 to the n. So now we clearly say, okay, so 7/8 to the n goes away and I'm left with 7/8 to the first. Which this is what I'm saying, if you like, you don't have to write this. If you're comfortable just saying, okay, nth power cancels, I'm left with 7/8 to the n. You don't have to write it this way. But okay, so 7/8 to the first, that's now just a constant term, so I could bring that out in front of the limit. And then I'm looking at the limit as n approaches infinity of n plus 1 over n. So this is a rational expression, same degree in the numerator and denominator. So the limit at infinity is equal to the ratio of the leading coefficients, which in this case is 1 over 1. So this limit is 1. So 7/8 times 1. So the limit is 7/8, which again is less than 1. So this series also converges, stepping on a cord, converges by the ratio test. Just note that if you work this out and your limit is equal to 1, then unfortunately ratio test is inconclusive and you'll go have to try another test. If the limit comes out, if this limit had been 8/7, 8 over 7 instead of 7 over 8, the limit would be greater than 1 and the conclusion would be that that the series diverges. But if the limit's less than 1, then the series converges.